Hello, ladies and gentlemen. So, I am not one to rhapsodize quixotic about the virtues of science. Um, Science has done some wonderful things for humanity. It's also done some things that have been kind of messed up. Um, Having said that, though, what we're going to talk about today, as far as I'm concerned, is very cool. It's a manipulation of nature, but it's very cool. Um, I don't know if you noticed, but when you are working in the lab, you have power supplies that are DC sources. Okay, if you need DC, you don't get a battery. You use these power supplies. They're driven by AC. You plug into the wall, you get AC out. AC, goes into the power supply. It probably there's a transformer that probably steps the voltage down. But by the time you get done, you have DC coming out. And the question arises, how does that happen? How do you take AC and turn it into DC? In the old days, it was done with vacuum tubes. So this is a schematic of a circuit with a vacuum tube in it. Okay. How is the vacuum tube built? Well, it's got two plates that are separated by a space. There is a heater circuit that's attached to one of the plates. If you've ever had the experience of turning on an old-fashioned radio, you'll know that it takes a while for them to warm up. What's warming up is the vacuum tube, specifically the heater circuit in the vacuum tube. Once that heater circuit gets red hot, it effectively boils electrons and it makes for free electrons in this region right here. So if you can do something that will actually motivate those electrons to jump this gap, you will get current in that circuit. So the question arises, how might you do that? So let's say that the AC coming into from the source, its polarity is like so, and let's say that makes this terminal positive. And that in turn would make this plate positive, which would motivate electrons to stream across, which means you got current. In other words, through this load resistor, you would get an output. When the polarity changed, now this is the high voltage side. That means this is the high voltage plate. Now the electrons are just going to stay home, so you're not going to end up getting current flowing. No electrons are going to go across the gap in that case, and so you're going to get no current in the circuit. Polarity goes back. So this becomes positive, this becomes positive. Now you have electrons streaming and you get output. Okay? So if you look at this, you may very well say, well, that doesn't look like anything that looks reasonable and familiar. I mean, I'm losing half my power. This thing is all lumpy. All of those observations are true, and all of those observations are fixable. But the point is that what you're looking at here is DC, in the sense that DC effectively is a situation in which current is only flowing in one direction in the circuit, and that's exactly what's happening here. Current's only flowing in one direction. Now, as I said, it's sloppy DC. It's lumpy. You're wasting, half of the cycle. But it turns out that there are ways with these vacuum tubes that you can get around that. You can make it so that you don't lose half, and you can make it so that you flatten it out. So there are ways to do this. So these devices are called rectifiers. And in fact, because you're only getting half of your wave, this particular one is called a half-wave rectifier. The devices that get rid of the lost power are called full-wave rectifiers. In any case, that's what they're called. Again, sloppy, but this can be taken care of. We'll talk about that later. These devices are still used in microwaves. They're also used in power amps, like if you have an electric guitar, the power amp devices that require or that generate a lot of heat will often use vacuum tubes. So what took the place of vacuum tubes were devices that were based on semiconductors. And so that's what we need to talk a little bit about. So silicon is an interesting atom in the sense that it has 4 valence electrons. The Lewis structure looks like this. I'm going to go ahead and identify those valence electrons with lines like so. And so this is what a lattice of silicon would look like, or at least a 2-dimensional version. Okay, so the question arises, what would happen if we plopped an impurity into the middle of this lattice? And I might add, doing that is called doping. So if we use, say, phosphorus, which has 5 valence electrons, what you'd end up with would be something like this. And what's interesting about this is these 8 electrons that you have here, they're all nestled nicely in the outer shell of the silicon atom. What's happening here is you have 8 electrons in what would be the outer shell, except you've got this 1 extra electron that is like 1 orbital out. And so it is not very strongly attached to the nucleus, which means it's really easy to get it to let loose. And so if you put this electron in an electric field, or for that matter, just thermal agitation could do it at room temperature. But if you were to do that, you could break it loose. Let me go back. You could break it loose and actually get it so that it could migrate through this structure. And if you did that, what you would end up with would be an insulating material that had conducting properties. Okay, and that's what a semiconductor is. So you put an impurity in, you apply an electric field, and you end up getting migration, hence semiconductors. So here you have it, your free electron, it's migrating. Okay, so because you have an electron, which is electrically negative, that's migrating, this is called an N-type semiconductor. And it's said to have what's called electron conduction. Okay, now the question arises, what would happen if the impurity didn't have 5 valence electrons but only had 3, which is to say if you used like boron. Okay, in that case, what you would end up with would be what's called a hole, which is an area where you'd like to have an electron, but you don't. If you put this structure in an electric field, what would end up happening is that if the electric field was to the left, electrons would want to go to the right. And so what would happen is that this electron would fill in the hole, but it would leave a hole behind. And then this electron would fill in the hole, but it would leave a hole behind. And then this electron would fill in the hole, but it would leave a hole behind. And so you'd end up with what's called hole conduction. And what's interesting about that is that if you had a hole here where you would normally have 8 valence electrons, but now you only have 7, this area right here would be a little bit more electrically positive than it would normally be. So as the holes would appear to be migrating through the structure in the direction of the electric field, that positiveness would be migrating through, and it would look like you had positive charges moving through the structure. So this is called a p-type semiconductor. And with p-type semiconductors, the kind of conduction that you have is what's called hole conduction. So if you were to have a test on this, this is Ms. Dunham's slide. One question would be, what is the difference between the 2 different kinds of conduction for the semiconductors? N-types have electron conduction, p-type have hole conduction. And another question could be, what is doping? Okay, it's the planting of impurities in a host material like silicon. Anyway, all right. So having said that, hypothetical question: what would happen if you took a p-type semiconductor and an n-type semiconductor and basically glued them together? Okay, so now you have what's called a p-n junction between the two. Here's the n-type, here's the p-type. And the question what would happen if you did that? And then proceeded to take that and stick it into an electrical circuit where you had a load resistor and an alternating current. So in this particular case, think about it. Here this side is positive, okay? The p-type, effectively, it's like it has positive charge that can move. The positive charge is going to end up being repelled by the high voltage terminal, so they're going to tend to want to go to the left. The electrons in the n-type are going to be repelled by the negative side of the terminal. So what's going to happen is that the electrons that are moving to the right are going to end up combining with the holes that are moving to the left, and they're going to basically just fill in one another. And it isn't going to take any energy really for that to happen because it's a natural thing to do. The positives and the negatives would tend to be attracted to one another. And so there's going to be very little voltage drop across this p-n junction, and pretty much all the voltage drop is going to be across the load. So you're going to get current. You're going to get current flow. When you have a big voltage drop across a resistor, that means you got a big current. Okay? And that's exactly what you're seeing in this schematic. So holes are going this way, electrons are going this way, very little voltage drop across here, most of it's across here, so you're going to get a nice big output across the load. When the polarity changes, now positives this way, the electrons are going to want to go in this direction, the holes are going to want to go in this direction, and what you're going to end up with is what's called a depletion zone. And across that depletion zone, it's almost like a break in the circuit. So pretty much all the voltage drop is going to be across here. There's effectively going to be no voltage drop across here. And effectively, you're going to have no output voltage. Go ahead and go to the next part of the cycle. You're now back to having current flowing easily. So you get output. So what you're looking at here is something that looks very much like the output from your half-wave rectifier. These things are called diodes. Okay, that's what they're called. This is the symbol of a diode for a diode right here. Okay, the arrow is pointing in the direction that current can flow. So in this particular case, current is trying to be pushed this way. It won't flow. Notice the stop. In this case, current's trying to be pushed this way. It will flow if the diode was set up like so. Okay. This is what diodes physically look like. They sort of look like a resistor in a circuit. They usually have a silver band at one end. The current function for a diode, the current characteristic, forward bias means that current is flowing. Usually you need about 0.6 of a volt before they'll actually turn on. And then once they turn on, if you increase the current, the voltage, you will increase the current through the element. In reverse bias, okay, so that's the stop part. You can make the voltage bigger and bigger and bigger and bigger and bigger, and you won't get any current until you actually break the voltage or break the diode down, at which time you get failure and then current will flow because you've basically destroyed the device. Turns out there actually are diodes that are designed to work in reverse bias. They're called Zener diodes, but that's not something you have to worry about. Interesting side note, these things, when they're in forward bias, actually dissipate energy. and they give that energy off primarily as electromagnetic radiation. If it happens to be in the optical range, you end up with what's called a light emitting diode or an LED. So probably some of you, if you've bought flashlights lately, they're LED flashlights. They're very efficient. They give off a huge amount of light. They don't take very much energy. In any case, this is the symbol for an LED. It's just the symbol for a diode with a couple of little squiggly arrows showing that the light is coming out. This is what an LED looks like. So the low voltage side, they're polar. Okay, current's got to go in the right direction. So current, the high voltage side, the anode is the longer end. The short side is the low voltage side. So current comes in the anode, comes out the cathode. Interestingly, if you were making your little robots and you happen to have been given a diode, an LED where its leads have been snipped, you can also tell whether you're looking at a positive or negative terminal. They actually flattened the side of the LED on the side of the low voltage side. So, and then again, cathode and anode. Why use one? You can convert obviously AC to DC. That's their main use. They are very easy. They're nice if you want to miniaturize things. If we were trying to make computers with vacuum tubes, the computers would be enormous. Diodes are tiny, tiny, tiny little things. So we had some problems though with diodes. Number one, you're wasting about half of your energy. And number two, the DC that you come out with is very lumpy. It doesn't look like what you think DC should look like. Normally, you would think that, a 3-volt DC source would be just, right straight across. That's not what you're seeing here. So the question arises, how do you fix that? And the answer is really quite clever. They use what's called a diode bridge. So if you track the current flow with this polarity through this diode bridge, current's going to come up here. When it gets here, it's not going to go to the right because of the block. It's going to go to the left. When it gets here, it's not going to go down because of the block. It's going to go across. So the current is going to the right across the resistor. When it gets here, it could go either way, but it's going to tend to go to the lower voltage side, so it's going to go down like so and out. Okay, so that's going to be what your current's going to look like. When the polarity changes, you're going to end up with something that's similar. It's going to come up, it's going to go out, but it's also going to go in, it's going to go through in the same direction. So through the load, the current's going in the same direction in both cases, which is DC, which is great. And so now you have what's called a full wave rectifier, because now you're not wasting half of your power. So the only other thing we have to worry about is how do you deal with the fact that it's lumpy? And basically what takes care of that is a capacitor. And so if you put a capacitor across here, what happens is that as the current is building up across here, the capacitor is charging itself up. And the current starts to drop. What will happen is that the capacitor will start to discharge through the resistor. And as it does, it will keep the current through the resistor up high. And so the net effect will be, instead of having the voltage drop down, the voltage will only drop very slowly because the capacitor has voltage across it and it's leaking its current out slowly. So its voltage is dropping slowly. And because it's in parallel with the load, the voltage across the load drops slowly. And so if you looked at what the voltage across the resistor looks like, it would look like this. Okay, this is called ripple. Except typically good power supplies have ripple of only like a couple of percent. And a couple of percent is so tiny that if you looked at it on an oscilloscope, it would just look like what you would expect DC to look like. It turns out there's one more thing that you can do with diodes, though, that you're going to find out about in the next screencast that is beyond really cool. So stay tuned.